Hello everybody, this video is on momentum and the conservation of momentum in two-dimensional systems. Previously, we discussed about the law of conservation of momentum, which states that in a closed system, the total momentum before and after a particular event, such as a collision between different masses, should be conserved. Now in this video, we'll talk about these events that are in two-dimensional settings. In two-dimensional scenarios, the total momentum is conserved in the x and y, or the horizontal and vertical axes, independently. So that means the momentum in the horizontal or x-axis is conserved before and after the collision or event, and the total momentum in the y-axis or the vertical axis is also conserved before and after the collision or event. So as a result, when you're approaching momentum problems in two-dimensional settings, you should always determine the initial total momentum in the x and y axes or directions separately, and apply the law of conservation momentum for each of the axes or dimensions. A 5 kg ball strikes a 10 kg stationary ball at 6 meters per second. After the collision, the 10 kg ball and the 5 kg ball will move at an angle of 30 and 60 degrees above and below the x-axis as shown. So if we draw a horizontal x-axis, the 30 degrees refers to this angle here, 10 kg ball after the collision, and the 60 degrees refers to this angle here for the 5 kg ball below the x-axis. The question asks, what are the final speeds of the two balls? Since this question involves collision between two masses, we can approach this by considering the law of conservation of momentum in two dimensions, the x and y dimension. Let's start with the x direction. In the x direction, the initial momentum before the collisions is due to the motion of the 5 kg ball only, as the 10 kg ball was stationary before the collision. So the initial total momentum in the horizontal direction is given by the 5 kg ball times by the horizontal velocity of 6 meters per second in the horizontal direction. And this is equal to the mass of the 5 kg ball multiplied by its velocity, let's call that Vax, in the horizontal direction, plus the 10 kg ball also multiplied by its velocity in the x direction, let's call that Vbx. So here in the equation, I've used Va to represent the 5 kg ball and Vb to represent the 10 kg ball. And I've also added little x to denote that this is a horizontal velocity in the x direction or in the x-axis. So this simplifies to 30 times by 5 Vax plus 10 Vbx. We can divide 5 on both sides to get 6 equals to Vax plus 2 Vbx. Let's call this equation 1, as I'll return to this later in my working out. All of these equations are derived from the conservation momentum in the x direction. So let's consider the same thing, but in the y direction. In the y direction, the initial momentum before the collision is actually 0, because the 5 kg ball was simply moving horizontally and the 10 kg ball was stationary. So we have 0 equals to 5 kilograms multiplied by Vay, the velocity in the y direction, plus 10 kilograms times by Vby, the velocity of the 10 kg ball in the y direction. And if we rearrange the equation, we'll get Vay equals to 2 Vby. Let's call this equation 2, as I'll return to it later as well. Previously, we said that the angle of the velocity of the two balls are 30 degrees above the x-axis and 60 degrees below the x-axis respectively. We can use these two angles to construct new equations that relates the x and y component of velocity of the two balls. For example, we can say that for the 5 kg ball, tangent 60 degrees is equal to the opposite velocity vector, which is the vertical component of velocity for the 5 kg ball, and this is represented by Vay, divided by the adjacent velocity vector to the angle, which is Vax. Tangent 60 degrees can be simplified as the square root of 3, and this is equal to Vay divided by Vax. So from this equation, I know that VAY is equal to square root of 3 multiplied by VAX. Now, I can construct similar equations for the velocity vectors for the 10 kilogram ball. I can say that tangent 30 degrees is equal to the opposite velocity vector, which will be VBY, divided by the adjacent velocity vector, which would be VBX. Tangent 30 degrees equals to 1 on square root of 3, and this is equal to VBY over VBX. Let's make VBY the subject here, so VBY is equal to VBX divided by the square root of 3. Now, I have two new equations in terms of VAY and VBY, so the vertical components of the two balls after the collision. I am going to substitute both of these equations into my second equation that I derived earlier. So, minus VAY, I know that this is equal to minus square root of 3 times by VAX from the first equation I derived over here on the bottom left of the screen. This is equal to 2 times by VBY. Now from this equation, I know that VBY is also equal to VBX divided by root 3. So this is equal to VBX divided by square root of 3. What I've done here is I simply replaced VAY and VBY in terms of VAX and VBX. I replaced the vertical components of the velocities by the horizontal components. Let's call this equation 3, just to distinguish this from the second equation. The reason why I've done this is so that I can now use the first equation, equation 1, and equation 3, and solve them simultaneously in order to calculate the values of VAX and VBX. I couldn't have done this without the third equation because in equation 1 and 2, I have 4 different variables. But now I have the third equation. If I compare this with the first equation, I have only got 2 unknown variables, which are VAX and VBX. So from the first equation, I can rearrange this to make VAX the subject, which would be 6 minus 2VBX. And then I can substitute this equation into the third equation. So substitute 1 into 3. Let's see what we get. So we have minus square root of 3 times by 6 minus 2VBX. This is equal to 2VBX divided by the square root of 3. If we multiply square root of 3 on both sides, this will get rid of the root here. So you get 3 times by 6 minus 2VBX is equal to 2VBX. Minus 18 plus 6VBX is equal to 2VBX. By rearranging this equation, I know that my VBX is equal to 4.5 meters per second. Now that I found the value of VBX, I can substitute this value of 4.5 into my first equation. So here I have VAX is equal to 6 minus 2 times by 4.5. So this will be 6 minus 9, and I get a value of minus 3 meters per second. Finally, to find the final speed of the two balls after they collided, I need to reconsider the angle at which the velocity vectors make with the horizontal axis. Let's start with the 5 kilogram ball. We know that the 5 kilogram ball moves at an angle of 60 degrees below the horizontal x-axis. And we've now just found that the horizontal velocity vector is minus 3 meters per second. So to find the hypotenuse of this vector triangle, I can say that its cosine 60 degrees is equal to 3 divided by VA, where VA is the final velocity or speed of the 5 kilogram ball. So VA is equal to 3 divided by cosine 60 degrees, which equals 6 meters per second. This is the final speed of the 5 kilogram ball. For the 10 kilogram ball, the velocity vector is above the x-axis of 30 degrees. And we found previously that VBX is going to the right at 4.5 meters per second. So cosine 30 degrees is equal to 4.5 divided by VB, which is the final speed of this 10 kilogram ball. So VB equals 5.2 meters per second. A stationary bombshell exploded to produce 3 fragments as shown. We've got fragment A, fragment B, and fragment C. We're given the mass of each fragment in the brackets, and then we are also supplied with the velocity of 2 of the fragments. The question is asking, what is the velocity of fragment C? This is also a momentum and conservation momentum question in a 2-dimensional system. So we can start analyzing the total momentum in the x and y directions independently before and after the explosion. Let's look at the momentum in the x direction. Since the bombshell was stationary before its explosion, the velocity of the entire bombshell is 0, and therefore its momentum in both the x and y direction initially will be both 0. So we can say 0 is equal to the total momentum in the x direction of all the 3 fragments combined. So for fragment A, the momentum after the explosion will be 0 because its velocity of 25 meters per second, it's heading upwards strictly in the vertical direction. For fragment B, it is moving at an angle of 45 degrees below the x-axis. So we can resolve this velocity vector into its horizontal and vertical components. The velocity in the x component will be 10 cosine 45 degrees, and the velocity in the vertical component heading downward will be 10 sine 45 degrees. We can then use these velocity vectors to find the momentum in the x and y directions respectively. So since we're looking at only the momentum in the x direction, for fragment B, its momentum will be its mass of 5 kilograms multiplied by its velocity in the x direction, which is 10 cosine 45 degrees. And since we're finding the total momentum, we need to add this to the momentum of fragment C. Let's call this PCX, the momentum of C in the x direction. Okay, let's analyze the momentum in the y direction. As we said earlier, the bombshell was initially stationary, so the total momentum in the y direction is also 0. And this is equal to the vertical momentum of fragment A, which would be simply its mass of 2 kilograms multiplied by a vertical velocity heading upwards at 25 meters per second. And we should add this to the vertical momentum of fragment B. This will be 5 kilograms multiplied by minus 10 sine 45 degrees. We've added a minus here because we've defined the upward direction as positive in the y-axis, which makes the downward direction automatically negative. And finally, we have to add the momentum of fragment C in the y direction. Let's call that PCY. For each of these equations, I can rearrange them to find the exact value of the x and y momentum of fragment C. So PCX will be equal to minus 50 cosine 45 degrees, which is minus 35.4 kilograms meters per second. And for PCY, this is equal to 50 sine 45 degrees minus 50, and that gives a value of minus 14.6 kilograms meters per second. Now that we have calculated the momentum for fragment C in both the x and y direction, we can draw this onto the vector diagram. So in the horizontal component, the momentum is negative 35.4. So let's draw a vector towards the left because this is the negative direction in my diagram. And the momentum here is equal to minus 35.4 kilograms meters per second. The momentum in the y direction is also negative 14.6 kilograms meters per second. So I have to draw a vector going down like this. So this is minus 14.6. From these two components, I can add the vectors to find the net momentum with the direction. Using Pythagoras theorem, my momentum will be equal to PCX squared plus PCY squared, or square root. Minus 35.4 squared plus minus 14.6 squared, or square root. This gives me a value of 38.3 kilograms meters per second. So this vector here, heading towards the bottom left of the screen, this is 38.3 kilograms meters per second. Since the question wants us to find the final velocity of fragment C, We can easily convert this into velocity by considering the equation for momentum. So the velocity will be equal to 38.3 divided by the mass of the fragment, which is 3 kilograms. This gives a value of 12.8 meters per second. As for all vectors, we need to also find a direction for this velocity vector. We can find a direction by finding the angle below the x-axis. We can say that tangent theta is equal to the opposite side, so 14.6 divided by the adjacent side of 35.4. So the angle theta equals 22 degrees. The final velocity of fragment C will be 12.8 meters per second at an angle of 22 degrees below the x-axis. This concludes the video on conservation momentum in two-dimensional settings.